All right, so does encrypted computation mean anything to anyone here? Well, some people. Hopefully it means something to all of you after this one. Just an extremely brief intro. I'm a senior researcher at Microsoft Research in the cryptography and privacy research group. So, you might wonder, what on earth am I doing here? Did I get lost? I did not get lost. Actually, this is some new research project that I've been working on with my colleague Wei Dai from Microsoft and a professor Beijia Hu from RIT and his student Asma Alofi. Of course, because Asma is like a PhD student, she's done most of the work here, and I'm kind of just reporting on the results. Also, thanks for Asma for letting me use her slides, some of her slides. Okay, so here's the agenda. I want to tell you what is encrypted computation, why it matters. I want to tell you about homomorphic encryption, which is a specific way of doing encrypted computation. And then I want to say, what does Spark have to do with any of this, and present some very initial unpublished results. All right, so whenever we in the cryptography and privacy research group, whenever we talk to customers and we talk to our colleagues in Microsoft, we usually always bring up these 3 stages of data privacy. Whenever you have anyone using the cloud environment for storage and computation, of course the data has to be encrypted and protected when it's being sent to the cloud. Well, luckily this has been figured out a long time ago. TLS is a really good way of encrypting data during transit, and it gives you authenticated communication too. Of course, also, while the data is being stored in the cloud, it should be encrypted, and this is very easy. We have AES, we have hardware implementation of AES in many CPUs, and it's like lightning fast. So you might just as well keep everything AES encrypted while it's being stored. Okay, but then comes the problem. Like, as soon as you want the cloud to do anything useful for you other than store the data, as soon as you want to do any kind of computation, the cloud operators have to somehow remove that encryption. And this means that they will have access to the key. This means that they will have access to your data. So how is it protected during computation in the cloud? Well, access policies, of course. This is how it's protected. Now, I wonder if there could be something better. Of course, this matters for many reasons. There could be, in various cloud provider companies, there could be insider threats. Of course, not at Microsoft. Outsider threats. I mean, of course, no one can break into Azure, but there are other companies who have weaker systems. Then there could be all kinds of data segregation issues when you have a lot of users using the same VMs. Then there's questions about regulations. If the cloud provider truly has access to your data, if someone there has access to your data, then they truly will have access to your data. And I mean, there might be some regulatory reason if this is, say, medical data or some other kind of data, that this is just unacceptable. Depends on the country. And finally, I would say that there's some liability concerns. There's situations like, what if the cloud provider just somehow accidentally leaks some of this data? Now they are liable for all these losses. This is something that would ideally be prevented. There's also some other reasons that are not mentioned here, but for example, you can think of situations where for example, US government goes to Microsoft and says, I want the data of this and this person. And then Microsoft will have to give that data. And Microsoft will have access to it because it has the secret keys, right? Of course, no company wants to be in this situation. So instead, here's what ideally we would have. This is encrypted computation. We have a privacy barrier between the user and the cloud, And we would want the user to be able to take their data, choose a key. So the user, the customer, chooses a key, encrypts their data. They can store the data in Azure long term. But now, as soon as the user wants any kind of computation to be done, it can just tell Azure, please do that computation, and Azure can do it without having access to the key at all. So the cloud can somehow compute directly on the encrypted data. Well, if you very carefully look, you can see that the color of the files has slightly changed, which is my indication of some kind of computation having been done on the data. Now, we send the encrypted result back, and because the customer has the key, the customer can remove the encryption and can get the result. Sweet. Well, I mean, it actually seems almost impossible, but in fact, there's many ways of achieving something of this style. And here's 3 ways. Homomorphic encryption is one. Secure multi-party computation is another group of cryptographic technologies that can do something of this style. And finally, secure hardware. For example, Intel has been developing this SGX instruction set that basically allows you to set up some kind of trusted environment sort of inside the CPU. That's extremely incorrect to say, but in some sense, security of this kind of system depends on the hardware implementation being correct and being somehow hard to, tweak with. You can't just go and like prod the CPU and somehow read some wires from there. Now, I'm going to focus on homomorphic encryption because, incidentally, it just turns out I've been working on this for the past maybe 4 years. So, now what is homomorphic encryption? It's basically what you saw on the previous graph. It's a system where it's like a new kind of encryption system, encryption scheme, that allows you to do computations directly on encrypted data. So you can have a data owner, someone who has the original data, and they have like some kind of secret key. They use this key to encrypt. They can, on the left-hand side, you can see the encryption kind of results in this nonsensical string, which is then being sent to an untrusted environment, and there you can process this encrypted data. For example, here we run it through 2 computations, times 2 and minus 5, and out comes another nonsensical piece of data. But once we send it back to the client who has the secret key, the data owner, they can remove that encryption and they can get the result. So often we get questions like, okay, so there must be some decryption happening there, but there isn't. Maybe a better way of thinking about it is that typically you can think of encryption as being, you take your files, you put it inside some kind of safe, and then you lock the safe, and now you can give the safe to some kind of storage, and your data is safe. But with homomorphic encryption, maybe you should think of the safe as being sort of soft, so that you can't see through it and you can't break it, but you can poke it. And when you poke it, the data inside it kind of like gets twisted and turned and somehow gets changed. And in this way, you can apply computations on the encrypted data without actually seeing what the encrypted data is and what the encrypted result is. So, good news, kind of, because this means that we can truly set up this kind of scenario where the user or the customer always keeps their keys. And in this kind of situation, we don't have to, the cloud provider has never to worry about something like GDPR because they simply do not have the data. We can get very strong privacy guarantees, and the third piece of good news is that there are open source implementations available. Well, one of them is created by our group. It's a library called Microsoft Seal. It's been publicly available for maybe 3 or 4 years almost now, but it's been open source MIT licensed only since last December. But Microsoft Seal is being developed actively today. Actually, just a couple of days ago, we released again a new version, and well, turns out we have to release some hotfix. Maybe tomorrow, but it's very good, and we pay a lot of attention to it. We take pull requests and things like this, and there's kind of the entire homomorphic encryption community is sort of now centered around a few homomorphic encryption libraries. So it's kind of a good community, and we develop these libraries together to some extent. It's written in C++ 17 and works with .NET. And it works also on all possible platforms, really. Well, maybe not some microcontrollers. That's going to be hard. OK, so what's the catch? Of course, actually, there's kind of a big catch, which is that encrypted computation is very complicated to do. It's not, if you think of a normal computation, you, for example, want to compute some kind of average of some numbers, or you want to evaluate some polynomial. You want to compare your value to 0, find the sign of your number. These kinds of things are very easy to do on unencrypted data, but on encrypted data they might not be easy. In practice, really, encrypted computations are only limited to addition and multiplication in many of these homomorphic encryption schemes. There are some other ones where you can do any binary operations, any bit operations. But then whatever computation you have to express it as bit operations first. And now it's going to kind of blow up. So we've taken this approach where we allow additions and multiplications to be done on encrypted data. It's also best only on small computations. So you, by small, I actually don't necessarily mean small. I mean having like not many consecutive multiplications. If you want to compute some degree 5 million polynomial, yeah, that's going to be a little bit hard. But computing the sum of 100 million numbers is very easy, because there's only one multiplication. The multiplications are sort of the difficult part here. Something that we're running into is that the programming model is very unusual. And it's still kind of hard for developers to learn. We're developing and creating and thinking about what kinds of tools could help with this. And finally, or maybe not finally, but there's a big slowdown. Encrypted computation is like maybe 1,000 times or some 100 or 1,000 times slower than unencrypted computation. So it's like significantly slower. If you have big data and you're struggling with that, there's no chance that you could do it like this. But that's not our approach at all. Our approach is more like, okay, so you have your table that is maybe very big, but maybe it has 10,000 columns. Let's only encrypt one of the columns. Maybe only one of the columns is critical to privacy. Maybe that's the social security number. Maybe that's some medical information or something like that. You don't have to necessarily encrypt everything, and you wouldn't do that because of the performance and of the data expansion kind of challenge that this technology brings. So encrypted data is also bigger than unencrypted data. Of course, I mean, we're working on these challenges, and there's constantly improvement and new development in this field. People are coming with new homomorphic encryption schemes and new techniques of making this better. Some other fun facts. There's no branching allowed, of course. Normally, if you create a program, of course you can like look at your value and you can branch. You can jump to a different point in the code. But you can't really do that on encrypted data, because otherwise you would be revealing some information about the data. So there is no branching possible. You can't have any conditional statements, really. You have, if you want to create some kind of like a if statement, you have to actually evaluate like both branches. So now if you think of some machine learning model such as random forest, where you have a lot of different paths, Normally, this would be maybe easy to evaluate, but now you would have to evaluate everything, because otherwise you'll leak information about what your values are. Well, I'm going to skip that. Now, you might ask, okay, so this guy is talking about something totally theoretical, and actually, I would imagine that most of you who have heard about homomorphic encryption have heard that it's totally impractical, that you can't really do anything with it. That was kind of the situation like from 2010 when it was invented to 2000 maybe 14 or 15 or so. But since then, there's been absolutely remarkable, improvements in the implementations and improvements in things like hardware acceleration. We just had a paper where we showed that with FPGAs, we can actually make this stuff over 200 times better, 200 times faster. That's kind of a lot. Now, something that we did, for example, that we have done, is evaluating neural networks on encrypted data. We've evaluated some medical predictive networks. So I believe it was like some liver cancer detection network. We've evaluated things like SqueezeNet on encrypted data. So what does this mean? This means that you take your data, you encrypt it, and you store it somewhere in cloud storage, for example. And at a later point, the cloud storage can evaluate their predictive model on your data. They get an encrypted result, which they don't obviously understand. They can send it back to you. So for example, you could do stuff like medical predictions. So I could set up some kind of medical predictive service. I don't have to reveal what model I'm using, but you can encrypt your data, you can send it to me, and I can kind of serve you with these predictions without seeing your data. I could do some financial predictions, maybe because, financial predictions are another very interesting thing here. For example, some credit risk predictions we've been thinking about a lot. Another fun thing, lookup tables. Something that, or kind of key value stores maybe, where I want to look up, what are the nearby breweries? It seems like beer is a common theme in this conference. So, what are the nearby breweries? But I don't necessarily want to reveal to Google that I'm looking up beer and I'm in Amsterdam. So maybe I can query some kind of private lookup table. I encrypt my query, I send it over. The lookup table is evaluated on the encrypted query. They get an encrypted result, which they can send back to me. This is actually possible. We can set up lookup tables, these kinds of private lookup tables of sizes like of billions. It's truly possible. And we can either retrieve if like a true or false if the key exists in the data set, and alternatively and additionally we can retrieve some data associated with that key. Well, this is kind of hard to see, but I really want to mention this. So this Financial Conduct Authority in the UK, this financial regulator, organized this tech sprint of combating financial crime, specifically anti-money laundering. The problem is that you have all these banks, and they all have different information about their customers. And now when some money mule goes to one of these banks and wants to open their 500th account, the bank is happy to open that account for them because the bank doesn't know that they've opened already like 499 accounts with the other banks. So in this tech sprint, in this like hackathon, we developed some solutions that can truly help these banks to kind of collaborate on their private data without truly sharing it with each other. They only get the result, and they can share the result, which is, this person might be suspicious, or this person might not be suspicious. But they don't share any other information about their customers. These things are truly possible. The biggest challenges in this one are that the banks don't actually want to know. I mean, it's actually it's true. Huh. Yeah, that was my reaction. Okay. So let me show a little demonstration. So, okay. So this is a little toy weather app that we created, and it uses the lookup table idea. So the idea is that I want to look up what is the weather in my location. How do I do that? I encrypt my location, send it over to a service, and the service compares my location to their weather data table and gives me back the result. But because my location has been encrypted, the service provider doesn't learn where I am. Toy example, like I said. But as you can see, we type in the zip code and we hit enter, and it's like on the left-hand side there's the server, and it's basically instantaneous. Of course, I can't remember how many zip codes there are, but actually the number of zip codes is kind of small. This is a very simple application of this lookup table. Another thing that we developed was a running app. There are all these kinds of running apps, and actually a company got into some bad publicity because they published their fitness app location data, and it revealed US military base locations. Now, how about we encrypt your location? When you run, we encrypt your location, we store it in encrypted form in the database. And once you request, okay, how much did I run in total on this and this day? What was my average velocity? It can actually compute all of that on encrypted data and just give you the encrypted results back. And the server never finds any information about anything. And you can pull some statistics from the server nevertheless. Well, okay, so Spark. Well, costly computation, large data size. This makes me think, well, actually, it didn't make me think of Spark, but it made my colleagues think of Spark. And indeed, this is what we started to look into. Would it be possible to use parallelizability and the big data storage that Spark can provide to kind of help with these performance issues of homomorphic encryption? Another reason is that a lot of Microsoft data is in Spark. A lot of our customer data is in Spark. Now, we would want to tell the customers, look, your data is already there. Here's some tools that you can use to build privacy-preserving application on top of the data store that you have. Turns out it wasn't totally easy because, well, I knew nothing about distributed systems. And the distributed systems people knew nothing about security. So it's just kind of an interesting thing to figure this out. We tried something not very efficient in the beginning. We tried to just pipe data to some customly written homomorphic encryption programs. Very easy to implement, very, very ugly. Have never seen anything uglier. But it's unfortunately impossible for people to use. And the performance is ridiculous because you're just like piping data back and forth through these programs. And it's like didn't work. Second approach. So let's just provide a high-level API in Spark for homomorphic encryption. Something that we can use through Python, Java, Scala. And this is something that there's a chance that data scientists and data engineers could actually use. We were able to get good performance from this. At least the performance is not like in the first solution. There is no huge data transfer overhead or anything like this. In fact, we are seeing the performance benefits of Spark. Of course, this was much more difficult to implement. So basically, what we did was we integrated Microsoft Seal with Spark. We are looking right now into all kinds of different uses of this. For example, we're building some data analytics and machine learning applications and tools on top of this. We have seen that we can speed up homomorphic encryption computations through this parallelization. For example, maybe the simplest possible thing, some huge average. You have a lot of different data stored across the different nodes, and you want to just compute the average. Can we make such a thing happen efficiently? Of course, everything is encrypted. So we're starting from these kind of basics. We also have to create some task and resource allocation algorithms for this stuff. And it's because I skipped something on one of the previous slides that I probably should explain now. So in homomorphic encryption, there is this situation that typically both your storage and your computation is extremely vectorized. So you can't just take one encrypted number and multiply that with another encrypted number. Or you can, but now you're wasting potentially like thousands of other kind of vector slots that you have in these encrypted registers. So there's no such thing as like a scalar multiplication, like one single scalar multiplication. There's always these vector multiplications that you do, and vector additions. And this is not just, in normal CPUs, you have vector registers and you can load values into those registers, and then you can do that computation. But it's very different because in this one, your unit is actually still that one single number. I mean, you can write bytes. But in this system, your unit of storage is that vector. So the storage and computation are both vectorizable. Now, if you think are vectorized, inherently vectorized, and that means that number one, you really want to leverage it. If your computation is not vectorizable, probably shouldn't do it, or maybe you should rethink it somehow. But now you can think of things like, what if I have a big database and I want to store one of the columns? You have to actually like split the columns into these vectors and store those vectors. And now you get into some challenges. What if I want to permute stuff? So in fact, this gets quite complicated to do. But we're working on it, and this is still like research in progress. I'm almost out of time here, but I guess I can quickly show this architecture. There's nothing too magical about it. Of course, Azure is backing everything here. But on top of that, we have the normal Spark stack. And we've wrote this Spark Seal API Java layer. And that communicates with the native layer, this libspark seal. And this wrapper between Spark Seal API Java and libspark seal it comes from Swig. And then at the bottom there is Microsoft Seal, which is also a native library, of course. We also wrote a Spark Seal plugin that can register some data types for you to make this much more convenient. So we can actually make it into like our goal is to make this into like a real data science-like experience where you can truly do things like, you can just say dot product and it does a dot product for you on encrypted data. And actually, our goal is also to make it so that you can just say that, okay, take an encrypted number and add that to another encrypted number. But you can see that this is not easy necessarily because of this vectorized nature of this encrypted computation. So we have to build some kind of abstractions there to make this possible. Yeah. All right, actually, just gonna say some things about future work. Well, as we've seen, this I didn't mention the name of the project, but the project is called Spark Seal. The project is not available yet, but the project will be available in the future under an open source license, hopefully, if everything goes well. And there's a lot of ongoing work that we're doing here, both in our group and then in collaboration with universities. One of them is that, of course, we're developing this Spark Seal, but we're also creating a compiler and a programming language for homomorphic encryption. This turns out to be extremely important because because of the complicated programming model. It's like extremely difficult to use right now, unfortunately. And it's very hard for developers to learn. So why not create your own programming language that kind of more closely models the programming paradigm, and then create some kind of compiler for that, optimizer for that. And this is what we're working on. Both some of this Spark stuff and this compiler stuff is going to be submitted to some conferences soon. Well, that's all from me.
Okay, so we have time for some questions.
Yeah, I was wondering, does there exist homomorphic encrypted programs that you can maybe, as a user, encrypt some data, have a program run a computation on it, and then reveal some other key of some sort so that you can prove that the result of that encryption is something, for example, that you have a high credit rating or something, so that, yeah, that a user may send their encrypted information, and then they can use that result of the computation to prove that they have a valid credit rating.
Right. That's certainly possible. It's possible that so you're the user, you're the customer. Your financial data is somehow held in encrypted form by some credit bureau or something like this. Now, this credit bureau, they can evaluate these credit risk models. They can get an encrypted result, and they can send it back to you. You have to decrypt it and send it back. But now you could very well ask, okay, well, I mean, how do they know that you don't just send them all good message, unlimited credit? But it's possible to attach some simple proofs to this, so that they will know that you truly sent the correct decrypted result back. Now, there's also something called functional encryption, where it's kind of a little bit similar. So I would encrypt my financial data, send it over, and they can't see my financial data. Of course, it's encrypted. They don't have the key, but they have a key for a specific computation. This is functional encryption. They have a key for a specific computation, which means that they can evaluate one single kind of computation, and they can get the result for that. So you don't have to go back and forth. But unfortunately, functional encryption is kind of very difficult. I mean, it's much more difficult than this. So the first approach is the best, I would say.
Thanks for the presentation. Really interesting. I wonder if you heard in your area also about machine learning approaches and how to use this for machine learning. I'll give you an example. You could have data set in one enterprise, you train the machine learning model on that, and then you just pass the machine learning model further, and then the other entity has additional data set and maybe trains either the model or has some sort of error model set, and then the error model augments the former model, and the process could go on and on and on. Something like a boosted, federated machine learning approach.
Yeah. That's what can I say? I mean, that's a real example. I know that, for example, I mean, we've looked into something like that, and Alibaba has looked into something like that. I'm not sure of Intel, but this is definitely, like, this is a good scenario, I think, and it's a real scenario that can work.
My only concern would be, what if somebody could reverse engineer the data from a machine learning model?
I mean, right. So that's always possible. whenever you reveal anything, any kind of result, unless it's somehow truly randomized, which you don't want your machine learning model to be, then it's going to reveal some information about the inputs, and there's nothing you can do about that. I mean, you could use things like differential privacy to maybe help with that, but that's a different conversation.
One technical question. In the past, with Apache Spark, we had some issue related to serialization and deserialization, because the PySpark environment works in Python and the other stuff of Spark works in Java, so you have to serialize, deserialize, and they invented Apache Arrow to avoid this kind of problems. So if I understood well, your things send data to a C++ library. So I think you have some kind of serialization, deserialization, and how you tackle this problem to avoid performance bottleneck.
Well, this was actually exactly the issue, one issue that we ran into, and I had to completely rewrite the serialization in Seal to allow it to serialize to a buffer directly, so we can set up some buffer in Java, and then we can serialize from native directly to that. That was my solution for the moment. There might be some better ways of doing it. There's a question.
Sorry. Okay, I have a quick question. So I try to understand what's the user, as a developer of your tool, what does the API look like? Is it standard Spark APIs, or is you provide the API for people write UDF type of things? I just try to understand, because you did not say, well, what is the user, what's your developer experience look like?
So this is not ready yet, and I think we're looking at APIs at many different levels. Like you can just work with RDDs if you want. This is of course the first thing that we did, but now we're looking into building something more. So I'm not quite sure where it's going to go, and we're struggling with some of these issues about this vectorized nature of the storage and the vectorized computation. So we need to sort of have a good solution for this, then maybe see what we can build from that. So I'm not really sure what it's going to look like eventually. But of course, like we would hope that this is something that's usable by data scientists and usable by like kind of also by maybe some on the homomorphic encryption side by normal developers.
Last question.
Hello. Yeah, for machine learning, one of the steps is feature selections. And I'm wondering, once you encrypt the data, do we keep the property of these features, and can we do like correlation? I mean, if the contributor will encrypt the data and send it to us, can we still apply
featurization?
Yeah.
I would say unlikely. It's the computation could be very complicated to do. I think the way to think about it is that in many machine learning tasks, of course it depends hugely on what it is, but in many of them you can just use some, for example, in some image recognition tasks, you can use just some standard featurizers. And maybe you can train those featurizers a little bit to specialize to your particular task. But you wouldn't necessarily want to like have to evaluate the full featurizers and everything on encrypted data. That might be too complicated to do on encrypted data. And besides, the featurized, the output of the featurizer is kind of, or the featurization is kind of to some extent reversible. So in fact, kind of the input and output have the same privacy challenges, and instead you could just featurize locally, maybe store those encrypted features.
Okay, and also there is a project called OpenMind where they basically they do federated learning, so they let you apply the algorithm locally and then just share the weight encrypted. This is maybe more easy to implement because you reduce all the computation.
It's a very different interaction model. So yeah, I mean, it's a very different interaction model. Here in homomorphic encryption, you get sort of like, you should think of getting encrypted storage plus computation. In the federated learning, it's like a fully interactive system. Here the idea is that I can take my data, I can store it somewhere, and they can store it indefinitely, and they can compute on it as much as they want. and I don't need to be involved in any way. They can share the results with me. They can publish the results on, their Google front page or whatever. But because it's encrypted, I don't care. With multi-party computation and techniques such as federated learning, it's like an interactive online process where you constantly exchange data to kind of train and achieve something. So it's a very different interaction model.
Okay. Thank you.
Thank you. That's it for this session. Let's thank the speaker one more time.
Thank you.